Spin and Cigar Smoke, the Stern-Gerlach Experiment by Joshua, Gad, and Lehna. Introduction. This topic is about the discovery of electron spin through Otto Stern and Walter Gerlach's spin and cigar smoke experiment, which demonstrated the fact that electrons have only two possible spins of positive half or negative one half. This was demonstrated by the fact that the electrons split into two exact streams instead of going in random directions during the experiment.
Otto Stern received his doctorate in physical chemistry at the University of Breslau in 1912, with his research on osmotic pressure. He was also Einstein's first pupil. He went on to teach theoretical physics in 1914 at the University of Frankfurt. He conducted his first experiment with molecular beams in 1920 and went on to conduct the famous Stern-Gerlach experiment in 1922. He then taught physical chemistry in 1923 at the University of Hamburg, and in 1933 he measured the magnetic moment of the proton. After World War I, he moved to America and taught physics at the Carnegie Institute of Technology from 1933 to 1945 when he retired. He was awarded the Nobel Prize for Physics in 1943 and received it in 1944 for his contribution to the development of the molecular ray method and his discovery of the magnetic moment of the proton.
The other half of this experiment, Walter Gerlach, was born in 1889. He received a doctorate in physics at the University of Tübingen in 1912 for research on blackbody radiation and the photoelectric effect. He went on to teach physics there, and then he performed the Stern-Gerlach experiment in 1922. Afterwards, his career took him to the University of Munich, where he continued to teach physics, and his interests were primarily in radiation, spectroscopy, and quantum theory.
The scientist and the experiment. This story actually ends up being quite fascinating, as both of them are credited on the research paper, but only one was actually present when the experiment was completed successfully. Both Otto Stern and Walter Gerlach created the spin and cigar smoke experiment and are credited on the research paper. However, only Walter Gerlach ended up being present when this experiment succeeded. This was because on his way to meet Otto Stern in Frankfurt, a railroad strike left him stuck in Göttingen for a day, giving him time to review and reattempt the experiment. Surprisingly, this attempt turned out to be successful, with Gerlach deciding to send Stern a postcard saying, "Bohr was right," and a picture of the electrons split into two beams. This is the experimental basis of the Stern-Gerlach experiment. The gray circle on the slide is the particle source, where the electrons are ejected from, through this magnetic field created by a north magnet and a south magnet. It's an uneven magnetic field, with the northern magnet being stronger than the south magnet, and there's a detector at the end which the electrons should hit after they pass through the magnetic field. The particle source will release a stream of electrons between the magnetic field, which should affect the direction of the electrons either towards the top of the detector or below.
Stern and Gerlach expected the electrons to behave similarly to magnets. With several different orientations of the magnets, they would be deflected slightly differently by the magnetic field and end up at varying heights on the other side. Stern and Gerlach suspected that if the distribution of electrons on the plate was at random heights, it would suggest that the spin of the electrons was also both varying and random.
Instead of the expected result, in which electrons traveled in many different random directions, Stern and Gerlach found that the electrons split into only two streams. However, this was still random. It could be thought of as a coin toss, where only two outcomes are possible, despite the random nature of the event.
To explain the experiment in layman's terms, if the spin wasn't quantized, the electrons would split randomly and have many different destinations, like a ball in a game of Plinko, where the balls would end up all over the place. However, the quantization of electron spin into either positive half or negative half means that there are only two possibilities, like a fork in the road, resulting in a clear split of the electrons' directions.
While Stern and Gerlach were conducting and fine-tuning the experiment, Stern could only afford cheap cigars which had a lot of sulfur in them. So when he looked closely at the plate to check for where the silver atoms had landed, the sulfur in his breath turned the silver on the plate into silver sulfide, which is black in color. The black silver sulfide molecules on the plate made it clear where the silver atoms had landed during the experiment.
The findings of Stern and Gerlach in their experiment provided the necessary information for Wolfgang Pauli to create his exclusion principle in 1925. Pauli's exclusion principle states that no two electrons can have the same set of quantum numbers. What this effectively means is that if two electrons are in the same orbital, they have equal and opposite spins. This is corroborated by Stern and Gerlach's result.
The outcomes of the experiment. The actual experiment was done with silver atoms to test the Bohr-Sommerfeld hypothesis that angular momentum was quantized. Bohr made the assumption that it was quantized in his model of the atom, but couldn't explain why that was the case. The Stern-Gerlach experiment showed that angular momentum was quantized and opened the door to our current understanding that electrons have a spin of plus half or negative half. It is important to understand that the experiment corroborated Bohr's hypothesis with experimental evidence, but still technically did not explain why angular momentum was quantized. A full quantum model which provided a reason for why this occurred was still years away.
Many of the concepts in Chem 163 deal with the quantum model of the atom. The spin of an electron is one of the 4 different quantum numbers that can describe the orientation an electron can have. If spin wasn't quantized, then it wouldn't be able to have a quantum number attached to it, and the concepts of orbitals that we derive from Schrödinger's equation wouldn't work. The anomalies and periodic trends are also explained indirectly by the quantization of spin. The Pauli exclusion principle stems from the work of Stern and Gerlach, and the Pauli exclusion principle states that each orbital can hold a maximum of 2 electrons that have different spins, described by 1/2 for one direction and -1/2 for the opposite direction. This explains the unexpected trend in ionization energy observed between elements in groups 2a and 3a of the periodic table. The valence electrons, or the electrons that are the farthest away from the center of the atom of elements in group 3a, are in an orbital that is further away than elements in group 2A. As electrons are attracted to the center of the atom, an ionization energy is defined as the energy required to remove a valence electron. It requires less energy to remove an electron from an orbital that is farther away from the center of the atom. Elements in group 5A have one electron in each of its outermost orbitals. However, elements in group 6A have an additional electron that fills up one of those outermost orbitals. And since electrons repel each other, it requires less energy to remove an electron from an orbital that is full or holds 2 electrons than an orbital that only has 1 electron.
In conclusion, the Stern-Gerlach experiment could really be considered a watershed moment in quantum mechanics. The results of the experiment opened the way towards our modern understanding of quantum theory. As was shown before, Bohr and Sommerfeld had just made the assumption that angular momentum was quantized. However, Stern and Gerlach were able to experimentally show that this was the case, which would allow further work to be done using this property in models. In fact, a lot of modern technologies such as nuclear magnetic resonance, optical pumping, lasers, atomic clocks, and brain imaging depend on the understanding of quantum theory, which has been developed in the years since Stern and Gerlach's significant experiment.